You can turn it on again. It doesn't make a difference.
Okay, okay. I turn again.
Yep.
Yes, but
Maria, are you okay being recorded? This talk?
yes, I am
And
okay.
public?
Okay. Yes.
Okay.
So now I will begin with the presentation. Is it okay?
Okay, so it's a pleasure to announce the speaker of this afternoon, first speaker of this afternoon. It's Professor Ruiz-Medina, and she's going to talk about functional time series approach for inference on multifractional partial differential equations. So please go ahead.
Thank you. And thank you to the organizers by this nice workshop, and also for this thematic beautiful, sorry, beautiful thematic subject, which is fractional partial differential equations. And also my thanks to not only to organizers, also to people which is here now. Okay, I am trying to move the, okay. The main topics we are going to explain and also to comments are some things related to inference on this kind of multifractional pseudodifferential equations. When we consider a starting point for inference, the observation or random realizations of this kind of spatiotemporal solution as a sequence of functional time series. This means that we can observe like a picture, a sequence of picture of maps of the surfaces in each time. For this, we are concentrated in the case where we are interested not only in estimation. In our particular case, we concentrate in minimum contrast empirical estimation. Also, we consider the case of long-range dependent, which is modeled in this framework in a heterogeneous way because it depends on the spatial resolution. So the range of dependence in time changes with the resolution in space. And also some examples as interesting cases are analysis to illustrate the potential applications of this framework. Also some statistical hypothesis testing about parameter are also established in the spectral domain, because the main contribution in the case of inference on this kind of model from the perspective of functional time series is that we are considering that our family is heterogeneous in the case where we are considering a finest resolutions levels. The topic is well known, and we know that when we are working with some kind of fractional pseudodifferential equation in time, which also could be fractional in space, we have some families of model. The most simple case is when we are considering a similar model. Then in that case, we have that the local scale is represented by the same parameter, the similar parameter. So the large scale behavior and the small scale behavior can be related. The non-similar case is also the usual and more realistic and flexible case when we consider that we have two different parameters or family of parameters which combine it for considering maybe asymptotics in increasing domain or in fixed domain, because fixed domain is given by higher resolution levels in a fixed domain, while when we consider the increasing domain asymptotic, we consider this kind of large scale behavior. The usual assumption we will consider is the stationarity in time, and sometimes when we are considering some manifold or some pseudo-homogeneous compact space, we also consider isotropic in space, but not necessarily. And the motivation is that the exponent which measures the long-run dependence is, as commented before, an operator which at different resolution level in space provides different range of dependent in time. And also we consider some extension and some several results in the current literature, which is also related with this kind of framework, before going to the detail of the approximation we consider in modeling functional time series with long range dependent. The motivation in relation to some examples which are related with some fractional multifractional differential equation is the well-known Carunen-Loewe expansion with the time-varying coefficients. As you see in the slide, Bn is a random process for each n, and this random process is considered to be stationary processes. We also have here the eigenvector of the spatial diffusion operator. This operator L can be a local operator or can be a pseudo-differential operator. Sorry, pseudo-differential operator. Or could be a pseudo-differential operator, non-local operator. In that sense, the framework is quite general, because the key thing is that we are modeling this kind of spatiotemporal covariance dependence through a series expansion where we have in Bn the long memory in time, but as you see in the slide, it depends on n, which is the resolution level in space. Thus, we are considering two well-known examples as motivation, which is the first example related to the well-known Mittag-Leffler solution to the eigenequation, but in our case, this eigenequation has a spatial varying, depending on resolution of the space, fractional integration, fractional derivation order, beta n. And in the second example, we consider that beta n is satisfied this kind of eigenequation, also this kind of fractional equation, where we have thus we understood this kind of operator, as explained later in more detail, some result in current literature, like in Marinucci, that we are this kind of operator where the fractional power is given by the eigenvalues of the operator A, which also admits an expression, spectral representation in terms of the resolution of the identity, which is provided by this kind of eigenvectors, defining the spectral point spectral in space of the spatial diffusion operator. Some special case, as commented before, in the current literature is, for example, the time-varying isotropic vector random field of compact two-point homogeneous space. This literature come to me thanks to Nikolai, which sent to me this kind of results, and which are very interesting, published by Malajenko in 2020, and it's related to this kind of expansion. But in that case, the expansion is given by this kind of Jacobi polynomial, and these results are given in theorem 4 and theorem 5 of this paper. And also we have that in this case we substitute the isotropy by the geodesic distance given in this kind of spaces, which are isometric to the sphere, for example. So in that case, we can consider also not manifold in that family. Also, we can consider the sphere, as mentioned here, where we have also some current results in this kind of space varying long range dependence in time given by the result from Marinucci 2020, again thanks to Nikolai, who sent also this kind of results. And also we have some example which can be motivated in case where we have a non-local operator in the case, because before we have local operator, we have the spherical Laplacian in the case of Marinucci, but here we have non-local operator where we have also multifractional equations as in this paper. The spatiotemporal spherical random field motivation in this paper in Marinucci 2020. In this case, we have as particular cases, as you know, the eigenvector and the spherical harmonics, and we have also this kind of angular spectra, and we have this kind of things defined in the Caron-Loeb expansion. And also we have that Marinucci considers this kind of long-run dependent depending on the spatial resolution. You can see here the beta L parameter, which in case beta L is in 0, 1, we have a long-run dependence, and this parameter depends on the resolution in space, which is given by the index L. And when we have alpha L, and then we have considering that beta equal to 1, and then we can consider alpha L in this interval to infinity, then we have short run dependence in time, but also depending on resolution in space. We also consider that in this case of this kind of families of dependence of covariance in time, we can consider that this kind of covariance is a particular case of Nating class when we consider heterogeneous Nating covariant families, which this kind of space varying long-run dependent. Also, in that case, we have that the inverse of this kind of integral operator is given by this kind of operator we have here. This kind of fractional differential operator depending on resolution in space given by this kind of expression, which provide the inverse of this kind of integral covariance operator, which depend on n or resolution. And here we have some misprint because instead of m is n in the spherical harmonic, which is diagonalized in the spectral domain operator A, defining the long-run dependent range in different resolution levels in the space. Here we have some example, but this kind of example is only to illustrate that the variation, because this is not real definition of the model in different, it's only a picture of this of fixed parameter, but it's only to motivate that the range is very sensitive to the new parameter, which in our case is the long-run dependent parameter, because when this new parameter in this parametric family change, also the range in time for t equal to 1, t equal to 500, or t equal to 1000 change quickly, as we know when also new parameter long-run dependent parameter change. Yeah, the same thing is shown when we plot all this kind of realization in the space for different locations. The next motivation is the case where we consider an extension of the well-known fractional kinetic equation, which was introduced to one version, one example, which is here at the end of the slide by Anna Leonenko in 2001. And they introduced this kind of model, and when we have this kind of fractional differentiation in time, and also this kind of non-local operator in space, and we have also that this solution in the form of this kind of Caron-Loeb expansion, where we consider the eigenvector of the negative Laplacian operator with Dirichlet conditions, and also we consider an extension when this kind of solution, instead of defining the dependent structure in time through this temporal coefficient, are given by this kind of equation where the fractional differentiation in time is given by beta n, which changes with the resolution in space, and also this kind of parameter is involved in the definition of the dependent range in time depending on space. So with this kind of example, we go to the framework of functional time series. In this kind of framework, we adopt, because the thing is that in the framework of functional time series, there are a lot of literature to approximate this kind of more complex model from complex observation like a curve of surface, which is the case we are considering here, or a sequence which are of the surface of curve is in a space, surface in time correlated, also define the functional sample. In that case, we are considering that in our application, the spectral theory, which was developed in 2014 by some people in Paranatol and Tabacoli, for example, they developed a spectral theory in the functional spectral domain in time, in terms of a spectral density operator, to analyze functional time series in weak-dependent case in a more flexible framework beyond the state space framework. In this case, the contribution is to consider the functional spectral domain for analyzing of this kind of functional time series, but with long-run dependence, which is, I think, still not developed, and this is one of the main contributions in the talk. Then we go beyond the previous framework of weak-dependent time series. We know that a lot of papers have been developed to model this kind of long-run dependent behaviors in time series, random field, or in different fractional or even multifractional differential model. The theories underlying the background to develop this kind of spectral theory is the operator value processes in the time domain approach. This operator value processes, when we consider linear functional time series, they define in the literature, in these references, that the exponents are given by operator, well-behaved operator, which are, of course, are bounded operator, normally bounded linear operator, that define the exponent of fractional integration in the time series. The weak-dependent scenario previously developed is based on, as commented before, in the functional spectral domain, based on the spectral density operator, the periodogram operator, and also the Kramer-Karunen-Loewe representation, which mainly has been developed by the papers cited here from the team of Naretos and Tabacoli. In the strong dependent scenario, the problem is that how we can define, how we can determine what are the optimal conditions to establish a family of operator with index the spectral, the frequency in time, and also that must be bounded operator, but not tray operator, like for example in the case of the weak-dependent processes. As you know, the absolute integrability of the covariance, of the absolute summability of covariance is short-run dependence in the real classical case. Here, the short-run dependent functional time series means that the trace of the covariance operator as absolute summable, but in our case, this condition is not satisfied to go beyond the short-run dependent case. So we have to replace this condition, a stronger condition, by other weaker condition, like in the classical case. And this is the difficulty to develop the tool for suitable definition of long memory with a singularity in the or unbounded operator in the zero frequency spectral density operator, and also with some good behavior to obtain the desired condition, for example, like that the bias of the periodogram operator goes in a suitable norm to 0 when the sample size is increasing, and several other properties that we now comment. And our choice in this sense is that establishing that we are working with a more flexible family of time series. We first consider in the upper part of this slide the classical conditions in functional time series, that because we have to work with the covariance operator in time, which are trait class. Trait class means that the sum of the absolute value of the eigenvalue is finite. And apart from this restriction, the rest of conditions are established to be minimal condition to go beyond short-run dependent. In that sense, when we define the spectral density operator, we define that this kind of series, here we have the functional Fourier transform, because here we have an operator and the equality is understood in the sense of a bounded linear operator. And then we consider that this series is convergent in the norm of bounded linear operator to define a spectral density operator as functional spectral Fourier transform. With a functional discrete Fourier transform of the data is also given in this slide in the upper part, and also is the direct extension, because here we have that xt is evaluated, as you know, in a function space that can be, in this case, a Hilbert space. Also, we consider that this kind of functional discrete Fourier transform is evaluated in the complex value version of the original Hilbert space, where we are considering the values of the time series lie. So we have this kind of property extended to this framework. Also, the periodogram operator is defined in a similar way by the tensional product of the surface or curves that define the discrete functional Fourier transform, and also the spectral density operator. In that case, when we truncate the expansion with respect to complex exponential, obtaining via Fecher kernel the periodogram operator, which is the covariance of the mean of this periodogram operator, gives this kind of a truncated version of the spectral density operator via Fecher kernel, as in the classical case. The only thing is that we are using here inequalities in that case, or in the space of in the norm bounded linear operator. Also, we have to extend some well-known results, like, for example, the first assumption, the minimal assumption, is that we have this kind of integrability of the bounded linear operator norm in the frequency domain for the family of spectral density operator, and that this minimal assumption, then we get that all family of operator, variance operator, as we know, are bounded operator. And also we have this kind of pulsable identity in terms of the Hilbert-Schmidt operator norm to work later. And also we deduce from assumption 1 all these conditions that allows us to work in this kind of functional spectrum domain with suitable conditions. Because we need that this family of operator, although they are not trace operator, they will be Hilbert-Schmidt operator almost surely in the spectral domain. Almost surely because we have one point with measure one, with zero measure point, then zero measure set. I'm sorry, that is the point 0 of omega equal to 0, where we have an unbounded operator, where we have this kind of singularity as in the classical case. Also, in that sense, under this kind of condition, the first result provides that some suitable operator norm where we can establish some kind or some extensions of the well-known Kramer-von-Mises type test for texting some expression or form to approximate the functional non-parametric form or parametric form in the two framework of the spectral density operator from the periodogram operator. These are some suitable expression for test statistics. Also, we have that the next assumption is how we can introduce in the spectral domain the long-run dependence. And then this is the condition we assume for defining long-run dependence in the temporal frequency domain in terms of the spectral density operator family we are considering, defining the functional Fourier transform of our covariance operator family. This is the condition, which means that we have here this kind of power, to the power, this operator, the operator A theta is a parametric operator, which define the long memory operator. And this operator is defined in the sense of exponential of operator, is well introduced in the literature via spectral theory, for example. And we have that our family of spectral density operator verify this kind of asymptotic behavior in the norm of the bounded linear operator norm or in the norm of bounded operator. So when the frequency goes to 0, we have this kind of behavior, which means that we are composing our family of spectral density operator with the inverse of this kind of operator, which is the operator M in frequency omega f, which is a regular part of the spectral density operator, and this kind of singularity, because here we are putting the inverse operator to verify that this kind of asymptotic behavior holds. Then we have also under the assumption considered that this family of operator indexed by the frequency in this interval minus pi as usually, they find the regular part, as we will see now in the sample, which are the regular polynomial, for example, or rational part without any singularity. The non-parametric part of our model, because we are considering a semi-parametric framework, the non-parametric framework is given by this kind of operator, M omega f, and this operator is assumed to admit a spectral representation in terms of a spectral family of operator value spectral measure that satisfy the conditions I'm going now to detail. And also this memory operator, which is also a parametric operator depending on some parameters, is also the admits kind of a spectral representation in terms of the operator value measure dA lambda, and also the lambda in here is the spatial spectra, and can be continuous spectra or can be point spectra. And in the case of point spectra, which is the usual case we are considering in the previous slide, we have considered in the previous slide, then we have that our resolution of identity, our operator value family is given by a spectral kernel given by the eigenvector of a spatial diffusion operator, and then we have also a spectral measure. But this is particular case. And also this kind of operator value spectral measure satisfy this kind of symmetricity, and also satisfy that kind of condition that are similar to the function distribution function property, which means that we are considered integration of operator value measure, and then we have this kind of continuity at the right, or we have also this kind of infimum in relation to the set. Or we have also that the limit of the families in the image of this kind of operator value measure is the 0 operator and the identity operator instead of the 0-1 interval. All the things are very similar. And finally, we consider also that under the previous assumption, as we are considering a common spectral operator value measure, or our operator involving the definition of a spectral density operator family commute, which is very common when we have this kind of property, or when we have that operator is function of another operator. But in particular, when we consider a common diagonalization in terms of a common spectral operator value measure. Then the previous definition of long-run dependent in the spectral domain with this kind of singularities now translated into this kind of behavior in the spectral domain. Here we have omega representative frequency, spectral frequency in time, but lambda is the spatial frequency, but not in the usual way. It's in the way I previously pointed out. The expression, formal expression of our operator family, spectral density operator family, characterizing our semi-parametric family of model functional time series models with long run dependence, is given by this m omega f lambda symbol characterizing our previous operator, and also by this kind of symbol, which is modulus omega temporal frequency, this to the power of this kind of symbol of our long memory operator, which is alpha lambda theta. And here we have the parametric estimation because we have to approximate this kind of function, which depends on the continuous spectral point spectra in space, hang on resolution in space, and also on a parameter theta to characterize this function, which define our long-run depending on resolution of the space. Other motivation also for defining somehow some alternative for hypothesis testing in semi-parametric way for functional time series, inspired in the methodology of Kramer-von-Miser functional test statistics. Here's an expression again with our semi-parametric model family and also with the periodogram operator. Also, we have here some conditions that we need to assume on our long memory operator, in particular on the symbol alpha lambda theta, which characterize this operator. This is a double bonded, this is a strictly positive operator, long memory operator, and also we have this bonded operator by this kind of upper bound, capital L alpha theta, lower bound L alpha theta. But this bandwidth allows us to prove some property which needs. Also, we have this kind of bonded operator in the non-parametric part, omega f. And the final assumption we consider to establish that this kind of spectral behavior in the functional spectral domain is equivalent to long-run dependent time in heterogeneous way is given by this proposition, where under the assumptions 1, 2, or 4, we have that this kind of behavior hold in the sense that our family of covariant operator or RT theta composed with the inverse of this kind of operator that I define in the slide, M till ETF A theta, which is defined via this kind of symbol, and with respect to the operator value spectral measure L E lambda, we have that this kind of convergence asymptotic behavior in when t goes to infinity hold. Thus, we have that the asymptotically we have equivalent behavior of our operator covariant family with respect to this kind of operator M tilde T F A theta composed with operator T to the power long memory operator A theta. Okay, A theta minus the identity on our Hilbert space. So after proving this kind of long-run dependent behavior depending on space, we have also some example. These examples are given here motivated, for example, to fractional integration of functional time series, but depending, as commented before, on the spatial resolution. For example, Robinson recently derived some framework, not in the spectral domain, in the time domain, for modeling long-run dependent functional time series. But in that case, we have that the fractional integration of this functional time series is given for a fixed order. Here we have, thanks to this a theta operator, we have this kind of variable long-run dependent range depending on resolution in space. These are the elements of the heterogeneous fractional version or functional version of FARIMA model, or FARIMA time model in functional context with heterogeneous fractional integration. Also, we have that this kind of regular path is given here when we consider the equation of this kind of polynomial. It's very similar. So we have in the definition of our operator spectral density family, we have the regular path, which is the equation of this kind of polynomial in the time frequency domain. And we have here also this path, which is defined in the time frequency domain, depending on omega, also in the spatial resolution domain, in the spatial point spectral domain, which is given by the symbol alpha L theta. This is the parametric symbol, which defines the spectral diagonalization of our long memory operator. So this part of the spectral density operator provides us the singularity at the origin for defining an unbounded domain, an unbounded operator in the in zero frequency. These are the constants and the details for definition of this extension of FARIMI models in functional context. Also, we have some more detail as how are the conditions that we are assuming to define this kind of model, fractional integrated model, depending on resolution in space. Okay, now some additional identifications that allow to show that we have this kind of long-run dependent or singularity at zero frequency depending on L in the given the resolution. The final state is that we have this kind of operator A theta divided by 2, which establishes our multifractional order of integration. Okay, we are going now to extend this kind of model to the case of discrete sampling of continuous process in time. Then we have this kind of spectral density family with this symbol F omega lambda theta, which depend on this kind of long memory operator, which is given by this expression in the frequency domain in time, depending on omega and depending on lambda, which is the spatial spectral domain as before. Here we have the regular part, and here we have the tapering function, which reflects the discrete sampling of our continuous functional processes in time. That are the conditions to establish in our symbols to obtain the previous assumption that ensure this kind of long-run dependent in heterogeneous behavior in time. And this is one example of this family, which is again the continuous versions, discrete sampling or continuous version of a rational family, which is fractional integrated by this kind of symbol. And then we have this heterogeneous fractional integration depending on the spatial spectrum defined in terms of symbol lambda. Also, we need for minimum contrast estimation that in our family the mean of our periodogram operator asymptotically coincides, as in the classical case, with the spectral density operators. This is given in this result where we establish that the norm in this case of the integrated mean of the periodogram operator converges to the spectral density operator in this norm of Hilbert-Schmidt operator norm. This is one of the results Also, we obtain that for establish a suitable framework for minimum contrast estimation in a spectral density family operator with semi-parametric modeling, some condition must be established, as in minimum contrast classical case or minimum or even in curval level divergent case. So we will consider that our symbol of our long memory operator satisfy these conditions like identifiability, and also we have that the parameter theta 0, which is a vector parameter, lies in the interior of a parametric space. We have that approximation, minimum contrast estimation based on a functional sample of psi t provides our approximation, parametric approximation of the symbol of a long memory operator. Then we have as in classical case, we have to define the weighted operator because we have long-run dependent, and then we have to ensure that we have a suitable spectral density operator family, because in that sense we have some unboundedness. And then we have this kind of modification of the operator measure by this weighting operator. And also this operator is like before, positive definite, and also self-join operator, and admit the same time of spectral representation in terms of our common operator value spectral measure, E lambda. After normalizing our spectral density operator family, because we can compute the integral of our spectral density operator family in the sense of our spectral value operator measure, and then obtain this kind of operator sigma quadrado theta, we have that the condition to establish what are our new normalized family of spectral density operator is given by this kind of expression, where we have that this is the normalizing operator, and this is the symbol defining our normalizing operator. Also, we have here the usual way when we have this kind of identity, we have that the integral of our normalized spectral density operator provide the identity operator. Like in the classical case, we have a spectral density, probability spectral density, here an operator value spectral density. Also, we have that for defining our contrast, our contrast functional, we have a contrast operator, which is given in terms of our spectral operator density family, and also we use the usual way of curval divergent definition of distance, which is the logarithm of this kind of normalizing spectral density operator family. And the final expression of our empirical contrast operator is for this minimum contrast estimation, the integral in this interval or frequency in time of the our periodogram operator with this kind of logarithm of the normalizing family spectral density operator with respect to this kind of weighting operator previously defined. Finally, we have this kind of spectral diverging operator, which define the contrast operator to establish the distance between the two parametric model and the possible or candidates. This is the true parametric model, which is given here by this kind of gamma omega theta 0, and we have composed this operator with the inverse of the candidates as approximation of a spectral density operator, which also index frequency in time omega and theta, with theta in the parametric space. We have again the integration, which is the effect to this weighting operator, and then we have definition of this kind of the divergent operator as the difference of the contrast the contrast functionals in this kind of contrast operator in the evaluated in the theta parameter minus its value in the true parameter. The symbol in our case of this kind of divergent operator is given here and in this part of the lower part of the slide, and here we have that this kind of expression is like curve level diverging, but weighting with this measure, this measure operator. And also we have this kind of interpretation that I commented before. So in the next slide, we prove that this kind of distance, statistical distance, is verifies the kind of condition of non-negative and negative condition to ensure that we have the minimum in the true parameter value, theta 0, and this is hence a good option to measure the statistical distance between the true model and the candidate model given by or defined in terms of the spectral density operator. So here we have also how to measure or how to define our loss function from this kind of divergent operator. So we consider, as before, the norm in the bundle linear operator, in the space of bundle linear operators. This is our norm to consider the minimum that gives us our approximation to the true parameter value, which is here hat theta t, depending on the sample size, in this case functional sample size, because our surfaces of psi t. So here we have that this kind of approximation of our symbol of our log memory operator via minimum contrast estimation, which is a parametric approximation, is a good approximation in the sense of it is weak consistency, and this weak consistency is proof under the previous assumptions 1 to 4. So we have that in this case this kind of limit holds, and also we have that as we wanted to prove before, that our empirical contrast functional, in our case our empirical contrast operator, also is consistent in the weak sense in the norm of the space or in the norm of the space given by the Hilbert-Schmidt operator in this Hilbert space. Also, we have here another alternative to measure distances in between operator defining the true model or the model, empirical model given by the functional data under the periodogram operator and the candidate. In this case, we have several options to define also some alternative for test statistics based on logarithm divergent functional. And these are some key references in this talk. That's all. Thank you for your attention.
Yeah, thank you very much for this very nice talk. Are there any questions or comments? So there seems to be none in the audience, as far as I can see. And let's see whether there are raised hands. Doesn't seem to be the case. Okay, then thank you very much again for this talk.
Thank you very much for listening to me. Thank you. See you. Okay, voy a dejar de compartir.
Okay.